All right, welcome to our 19th lesson of the semester here in Calculus 2. So today we're going to continue our quest to learn a bunch of different series tests. So we know, given any particular series, whether or not it's going to converge, meaning the numbers will add up to something nice, or diverge, meaning the numbers will add up to something that goes off to infinity or maybe bounces around indefinitely. And remember, the main goal for this, the reason why we're doing series is so we can write functions as these infinitely long polynomials. And according to at least what I said earlier, that's a good thing because polynomials are nice. And sometimes you get really complicated functions you don't want to deal with, and you'd rather just deal with a polynomial instead. So we're going to get to that part later, but for now, we need to learn the background material of whether or not series converge or diverge. So today, what we're going to do, today's lesson is going to talk about what's called the direct comparison test. And then we're also going to review some limits. So we're going to review things like L'Hopital's rule and things kind of like that. So we'll be doing that kind of closer to the end here. All right, so direct comparison test, what is that? Well, last time we learned about the p-test, right? So the p-test said if we have a series that looks like this, the sum from 1 to infinity, 1 over n to the p, if p is greater than 1, the series converges, and if p is less than or equal to 1, the series diverges. Okay, that's all well and good, but then what if I maybe look at a series like this? 1 over n squared plus n plus 1. Now, in the long run, we know that squares go to infinity much faster than linear terms, and then this isn't going to infinity at all. So in the long run, this sequence's behavior is going to be dominated by this n squared here. So you might think that since this is going to act a lot like 1 over n squared, then our p would equal 2, and so this would pass the p-test, and this would converge. But unfortunately, we can't use the p-test because of this stuff right here. So we can't directly use the p-test here, which is kind of unfortunate because that was a good hunch. That was a good hunch there. It is going to act a lot like 1 over n squared. And because 1 over n squared converges as a series, then this will converge as a series as well. But what we kind of just did was we picked another series that we know more about, and we likened it to the one that we have. We saw what the one we compared it to did, and the one that we have originally will do the same thing. That's going to be the crux of the direct comparison test here. We find an easier series and compare it to our original series. So that's going to be the idea of the direct comparison test. And why is it not just called the comparison test? Well, there's actually going to be 2 different types of comparison tests, but we'll get to the other type next time. All right, so let me state what the direct comparison test is. Okay, so consider the series, the sum from n equals 1 to infinity of a sub n, where a sub n is greater than or equal to 0. So remember how last time we had the conditions for the integral test with positive, decreasing, and continuous? So in this case, we're just only going to have one condition. We just need to be greater than or equal to 0 for this to work. So we can only do that on non-negative series. But if we have a non-negative series, then we can use direct comparison. So consider the series AN where the sequence we're adding up is greater than or equal to 0. Then one of 2 things happens. If there is a Bn, which is also greater than or equal to 0, such that An is less than or equal to Bn, and the series for Bn converges, then the series for AN converges as well. All right, and then what's the other thing that could happen? If on the other hand, there is a Bn such that An is greater than or equal to Bn, so it's the other way, and the sum from 1 to infinity of Bn diverges, then An diverges as well. There we go. That's going to be the direct comparison test. All right, so that was kind of a mouthful, so let's put this in layman's terms here. So what we're doing, this is our original series right here. This is the one that we really care about, and we want to figure out whether that one converges or diverges. So what we're supposed to do is we pick a Bn, which is often called the comparison. We pick a Bn that's going to be similar to An, but it's simpler. So for example, up here, something that's kind of similar to this, but it's a bit simpler, would be 1 over n squared. So we pick a Bn like that. Now, if we want to show that An converges, if we can see that our comparison is even bigger than An, and the comparison converges, then the original one converges as well. Now, why is that going to be true? Well, let's say we're adding up a bunch of numbers that are even bigger than the numbers we care about, right? All the numbers in this comparison are going to be bigger than the numbers we care about. If we add up those numbers and that goes to something finite, then if we add up smaller numbers, that's going to be finite too, because even the bigger ones ended up being finite here. Why include the part where Bn is greater than equals? I mean, you technically didn't need that. Yeah, you're right. So we could have omitted this part right here. It's just kind of a reminder that everything we're working with here is positive for that question. All right, now what about the flip side? So let's say we suspect that our original series is going to diverge. Then what we do is we pick a Bn that's even smaller than our original series, and we add that up. And if our comparison, the smaller thing, if that adds up to something that diverges, then if we add up the bigger thing, what do you think is going to happen then? It's going to diverge, right? So you're going to be even bigger than something that already diverged. So that means that the original one will diverge as well. So that's kind of the reasoning behind the direct comparison test here. All right, so let's go ahead and take a look at an example of this. And a good example would be the one that I introduced class with. Is the bigger one just increasing faster or something? No, it literally needs to be bigger for the for this to work. So the nth number in the list for Bn always needs to be bigger than the nth number in the list for An, and vice versa, right here. But that, hold on to that idea though, because that is going to be something we're going to be using in the future. So increasing faster. So example 1, let's take a look at the series I wrote in the beginning here. Okay, so this guy is my An. Now we need to make sure that this is greater than or equal to 0. So I'm just going to put a plus sign for that. So is this greater than or equal to 0? Well, this is always going to be positive. This is positive when we put positive stuff into it, and these are positive. So yes, we're going to satisfy that. Okay, so then now that means that we're ready to use the test. So the thing about the comparison test is that there's a little bit of creativity involved with it. You need to pick your comparison sequence. So now the comparison, there is a method to it. What I usually like to do to pick the comparison is I pick the dominant term on the top. Well, there's only one term on the top, it's 1. And I pick the dominant term on the bottom, which is n squared. And by dominant term, I mean the thing that goes to infinity the fastest. So n squared goes to infinity faster than n does, so I'm going to pick n squared. And it's pretty common to make your Bn just be the ratio of those. So my Bn is going to be 1 over n squared. All right, well, let's see here. So since my Bn is 1 over n squared, let's take a look at what the series Bn does. So if we add up 1 over n squared, is this going to converge or is this going to diverge? Yeah, this one, so we can use the p-test on this, right? So we can use the p-test here. And since p is bigger than 1 because it's 2, we know it's going to converge. This converges by p-test. All right, well, that gives us a pretty big clue. So since our comparison converges, well, we suspect that our original series is going to converge as well. Now, if we want to do convergence, then we're going to look at this first condition here. So we want our original to be less than or equal to our comparison. All right, so we need to show that this is true. So how do we do that? Well, let's start with AN. What we're going to do is we're going to construct what's called a string of inequalities, starting from here and hopefully ending here. And we want each of them to be a less than or equal to sign. So if we connect them all together, what's at the end is greater than or equal to what's up here. Okay, so then that means that at every step of the way, if I'm going through a less than sign, that means the thing on the right's got to be bigger. So I need to work on ways to make this bigger, but then also look more like this. That's kind of the name of the game here. All right, now how can I make this bigger? Well, let's see. You can make a fraction bigger by making its denominator bigger, I mixed that up. By making its numerator bigger or making its denominator smaller. So a way we can make the denominator smaller, just like Jordan says, is we can get rid of the plus 1. So we have 1 over n squared plus n. And the reason this is true is because of smaller denominator. Okay, well, that seemed to work pretty well, right? So we can make this even bigger if we chop off the n down there. We make our denominator even smaller. And then lo and behold, we end up at our bn. So we see if we connect all of these inequalities together, we have an is less than or equal to bn right here. So since we satisfied this and bn converges by the p-test, we know that our original series, 1 over n squared plus n plus 1, converges by the direct comparison test. Now, it kind of sucks to write out 3 or more words, so let's just call this DCT. If you write down DCT, well, I guess you're not going to write down anything for me, but if you ever say DCT or something like that, I'll know what you mean. What about at negative terms? Well, remember, yeah, this stuff only works if everything is non-negative. If we introduce negative stuff into there, then all this is out the window. It's not going to work. You can actually make a version that only works for strictly negative things, like everything's below 0, but I don't want to talk about that because that's just going to flip all the inequalities and it's going to be really confusing. So we're just going to stick with positive stuff. All right, let's do another example here. Then I'll have you guys do one. What if an was 1 over n minus 1 over n squared minus n? Yeah, we'll get to that in a little bit. That's an interesting scenario. All right. You guys have a lot of good ideas today. So let's say we have the sum from n equals 2 to infinity of 2n plus 1, and then we divide that by n squared minus n minus 1. So we want to think about what this is going to do as a series, and we want to show what it's going to do as a series by using the direct comparison test. So we're going to use the direct comparison test here. Okay, now let's see here. Usually what I like to start out doing is I like to kind of make a guess as to what my series is going to do. And usually my guess involves looking at the dominant terms of the top and bottom. So my dominant term up here seems to be 2n, and my dominant term down here seems to be n squared. So I think I'm going to take a look at 2n over n squared. Now, of course, I can simplify this to 2 over n. All right, so let's take a look at that as a series. So we have the sum from n equals 1 to infinity of 2 over n. By the way, so constants in a series, I don't know if I explicitly mentioned this or not, but you can move constants out of a series. So this is the same thing as 2 times the sum from 1 to infinity of 1 over n. Now let me ask you guys this. What is this going to do as a series? Is this going to converge or is this going to diverge? Oh, wouldn't it have to be from n equals 2? It technically doesn't need to be the same starting index, but yeah, I usually just use the same ones. Thank you. Yeah, it's going to diverge, right? And how is it going to diverge? Well, this is technically 1 over n to the first power, right? And if we go back to our friend, the p-test, all the way back here, we see that if p is less than or equal to 1, we're going to diverge as a series. So remember, just because this goes to 0 as a sequence doesn't mean we're going to converge. This is going to diverge by the p-test. Wait, so why did we start at 2? Well, we had to start at 2 here. Actually, why did I make this start at 2? Oh, I made this start at 2 so it would be positive. Yeah, because if we start at 1, then we're going to have a negative 1 there. We can't do it. So that's why I decided to start things at 2. Oh yeah, so that's another thing to be aware of. We need to make sure that the top is positive and the bottom is positive. But as long as our n's at least as big as 2, that will be the case. So we can actually use the test here. All right. So since our comparison, our most obvious comparison where we pick the leading terms, since that diverges, that's a pretty strong hint indicating that our own series will diverge as well. So let's see if we can show that. So what we need to do is we need to construct a string of inequalities, kind of like before. But the difference this time, and let me bring this back, is if we want to show divergence, then we need our an to be bigger than or equal to our bn. So this time our inequalities are going to go the other way. So I'm going to start at an, and an is going to be the big one. And we're going to need to keep getting smaller and smaller until we get to bn, which is 2 over n right here. Okay, now remember, the way to make a fraction smaller is to make the numerator smaller or the denominator bigger. So let's see. I think there's a pretty clear way to make the numerator smaller. We just chop off that 1. Okay. Not quite there yet, though. What else can we do? Oh, what was that? Yeah, so we can get rid of the n down here by adding it in. So we add n to the bottom, and we make our denominator smaller. Or sorry, bigger. Oh my God. I can't mix that up today. So since we added something to our denominator here, our fraction overall got smaller. And then we could do the same thing again here. We can add 1 to our denominator, and we get even smaller. And then finally, we could do our little cancellation, and we arrive at our destination, which is bn. So what we're saying here with the direct comparison test is that we know that as a series, 2 over n is going to diverge. Now we have a series that's even bigger than that. So if we're adding up numbers that are even bigger than the ones that are already adding up to infinity, then there's no way this is going to be something finite. It needs to go to infinity. So we would say, therefore, the sum n equals 2 to infinity, 2n plus 1 over n squared minus n minus 1 diverges by the direct comparison test right here. Why did I get rid of the n? So I was adding something to my denominator to make it smaller overall. That's why I decided to get rid of that n. All right. So now I want you guys to give this a shot. And this example is going to be a little bit different from before, but I think you guys can still do it. Okay, so what I want you guys to do is use the direct comparison test on the sum from n equals 1 to infinity of the absolute value of sine of n over n squared. And I want you to determine if this converges or diverges. Now, if you add something to your denominator, that's going to make it smaller because you're adding it to the denominator. If it converges, is there a way to figure out what it converges to? Most of the time, no. The only series that we can reliably know what they converge to are geometric and telescoping series. But like, for example, if this one ends up converging, then I have no idea what number that's going to add up to. I mean, you could approximate it with a computer, but it's hard to get an exact formula. What do you mean by adding one? So if we go back here, I'm adding stuff to my denominator. So between here and here, I add an n to the denominator. So adding something to the denominator makes your fraction smaller. And then here I added 1 to the denominator, like that. Another way of thinking about this, you can also use concrete numbers. So for example, 2/3 is going to be greater than or equal to 2/4 because I made my denominator bigger. That's kind of a more concrete example right here. Why don't you use your worksheets and write out on those? Just in case I have something I want to say that's not on there. I don't like being bound by that. Got that it converges. All right, we'll see. What would you compare it to? Well, think about what the top is bounded by. What's something that's always going to be bigger than absolute value of sine of n? So the weird part about this is the absolute value of sine of n, right? So we should probably replace that with something to make it simpler. Think about what sine of n can never be bigger than. Is it 2 pi? Well, I agree sine can't get as big as 2 pi. Yeah, so why don't you try replacing it with 1 and see what happens? Are we going to end up using the p-test? Yeah, we're going to use the p-test on the comparison to see what that does. Yeah, that's right, Amber. You guys have done a minute or so, and then we'll go over. Seems like the consensus is converging. Yeah, that's some good intuition. All right, let's take a look at this guy. So we need to use the direct comparison test, meaning we need to pick a Bn to compare it to. So absolute value of sine of n. Well, sine normally, without an absolute value, bounces between -1 and 1, right? So with an absolute value, what are the numbers it's going to bounce between? Oh, Christopher already said the answer right there. It's just going to bounce between 0 and 1 because it can't be negative anymore because of the absolute value. So that means that this is never going to get any bigger than 1, right? And 1's a pretty simple thing to compare it to. So I'm just going to compare it to 1. And I'll keep the bottom as n squared. All right. So this is going to be my comparison here. And I was inspired by the fact that this will never be bigger than 1. It's bounded. And if I look at this, this converges by the p-test. Okay, so this is giving me my hint that our series is probably going to converge as well. We need to see that for sure. So remember, if we want to show convergence, we need to start with our original and then show it's less than or equal to Bn. Because if we're less than something that's already only going to a finite number, then we have to go to a finite number as well. All right, well, this is actually going to be the shortest inequality we're going to do today, because absolute value of sine of n, we just talked about this, the numerator is always less than or equal to 1. So we can kind of just write down the answer for this one. So we have absolute value of sine of n is less than 1, so we replace that with 1, make it bigger, and then we get Bn. So we see that our original series converges by the direct comparison test. There we go. So the moral of this story is if you see absolute value of sine or also absolute value of cosine as well, just replace that with a 1 and see what happens, because those are going to be bounded by 1. All right, let's do another example. All right, so this example, can we, and I'm going to put in parentheses, easily use the direct comparison test to see if the sum from n equals 1 to infinity of 1 over n squared minus n plus 1 converges? All right, well, I don't know. Let's give it a shot. So what do you think I would compare this to if I had to compare it to something? I had to use the direct comparison test. Yeah, it's so we're going to pick the biggest terms on the top and bottom. So we have 1 and n squared here. Oh, this is 1 over n squared minus n plus 1. Yeah, so we're going to compare this to 1 over n squared. So if we start here, we know that we just saw a few times by now that 1 over n squared is going to converge as a series. So we think this probably will converge too. So what we need to do is we need to have a string of inequalities where we keep making this less than or equal to until we get to 1 over n squared. Well, one way to make this bigger and approach 1 over n squared is to subtract 1 from the bottom. So we end up with this right here. But now there's a problem. So normally you might expect, okay, well, we'll just add n to the bottom and then that will get us there. But the problem with adding n to the bottom is that it makes the result smaller, not bigger. And that means we're going through this in the wrong way. We need the next thing to be even bigger right here. Yeah, so Nick has the right idea. And I think actually someone else earlier in the class was poking at this too. What if we had 1 over n squared minus n? What's going to happen here? Well, the thing is that we can't easily do it. Maybe there's some, kind of crazy way we can show that this would be less than 1 over n squared eventually. But yeah, we can't easily use the direct comparison test to do this. because the inequality would go the wrong way. We can't add n to the bottom and make it bigger. That'd be like saying if you had 1/3, then it's going to be less than or equal to if you add something to the bottom, like 1/4, or you add 1 to the bottom. So that's not going to work, and then this is not going to work either. All right, and then how about this? The sum from n equals 2 to infinity of 1 over n minus 1. Well, the same thing is going to happen here. We have the sign going the wrong way, so we're not going to be able to do this. So this kind of exposes, this is frowny face, this exposes a limitation with the direct comparison test. So we effectively need all of the signs to line up in the right way in order to do this. So we can do one of these inequalities right here. Wait, why can I add n to the bottom? Because if I added n to the bottom, I would be smaller, but my goal is to try to get bigger. It's kind of like this. If I add 1 to the bottom here, I get 1/4, but 1/4 is not bigger than 1/3. Wouldn't n squared be bigger than if you subtract n going backwards? I mean, if you're willing to go this way, then yeah, but we're trying to get bigger there. So that's not going to work if we want to get bigger. But fortunately, we're going to have a way to get around this where we won't have to worry about this issue at all. So there's this limitation where we need the inequalities to, we need our inequalities to go the right way. So if they don't go the right way, what are we supposed to do? Well, this is where we use what's called the limit comparison test. Okay, so what is the limit comparison test? Well, the answer to that question will happen next class. So next class is going to be where we're going to focus on the limit comparison test. But the thing is that the limit comparison test requires us to do limits right here. So we should probably review some limits. And I know if you took Calc AB, I don't think they necessarily go over L'Hopital's rule. Is that standard for A? Oh, it is? They do that now? I didn't do that when I was in Calc AB. Oh, geez. All right, well, anyways, well, regardless if you went over or not, we're going to review it. So we'll make sure we're fresh on our skills here. So we're going to spend the rest of the time reviewing limits here. Although I did see a good question a few lines back here. How do I know whether to see if something's bigger than or smaller than? Like, how do I kind of know what to do in general with this? For these, I would always just kind of check the dominant terms if you can. So if there's more than one term, I would always check the dominant terms. If there isn't more than one term, I would try to take a complicated thing and make it simpler. So I knew I could just replace this with 1, because this is never going to be any bigger than 1 right there. So that's kind of my reasoning for that. All right, so let's review some limits here. Let's see. So the main thing I want to review with limits is L'Hopital's rule. So for those of you who haven't seen it, or maybe you haven't seen it in a second, let's talk about it. So L'Hopital's rule, or El Hospital's rule, if you like to butcher things. So if you are evaluating a limit of the form, limit as x goes to a of f of, this is a, f of x over g of x, and one of these situations applies. The first situation is the f of x on the top is going to 0, and so is g of x. So if they're both going to 0, or if both limits go to plus or minus infinity. It doesn't matter which sign it is. It just you need to be going towards some type of infinity. So if we have both of those things being true, and the limit for f prime of x over g prime of x exists, so if that's an okay limit, then the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x right here. So effectively what you're doing with this is you're replacing both the top and bottom with their derivative functions. And I want to emphasize, we're not doing the quotient rule here. It's actually easier than that. We're just doing the derivative of the top divided by the derivative of the bottom. Effectively, the way this works is it's almost like a tiebreaker. So both of these are going to infinity, right? Or maybe they're both going to 0. Now, what the derivative tells us is how fast they're going there. So it's sort of a tiebreaker. If you're both going to the same place, you see which one is getting there faster. And remember, you could also use L'Hopital's rule multiple times. So if this one doesn't work, then you can move on to f double prime over g double prime. And you can do this as many times as you need to or want to get to a satisfactory limit. All right, so let's do some practice with this. All right, so let's compute this limit. The limit as x goes to infinity of x squared plus x plus 1 over 2 to the x power. All right, now if we try to just plug in the limit and see what happens, well, the top is going to infinity, right? But then 2 raised to a larger and larger power, that also goes to infinity right here. So that means that we could use L'Hopital's rule. Now it's customary, you don't need to do this, but I like to show that I use L'Hopital's rule by putting a little LR above my equal sign, but you don't have to do that. So I do the derivative of the top. I got 2x plus 1. And I do the derivative of the bottom. Does anyone remember what the derivative of 2 to the x is? How do you do that? That's right. We stick an extra natural log of 2 in there. And if it was like 3 to the x, we would have had an ln of 3. If it was 4 to the x, we would have an ln of 4, and so on. Okay, now let's reevaluate. So we hope that our limit gets better when we do this. But it still seems like the top is going to infinity, and the bottom is also going to be going to infinity as well, because we still have that 2 to the x right there. So what we're going to do is we're going to try it again. Like I said, we could do this as many times as we want or need to get where we want to go. The derivative of my top is now 2, and the derivative of the bottom, well, I simply multiply by another natural log of 2. So I have natural log of 2 squared now. We have lots of 2's in this. All right, now let's take a look at this limit once again. So on the top, I have 2. So definitely 2 is not going to infinity. 2 is 2. So we're definitely not going to be using this again. But our bottom is still going to infinity. So if we have 2 divided by some massive number on the bottom here, what is that limit going to be? It's going to be 0. That's right. So that's going to be the end result of using L'Hopital's rule. Another way we could have done this is we could have invoked the hierarchy of functions. Remember we talked about that a few classes ago. Polynomials go to infinity more slowly than exponentials do. So if you have them kind of competing in a limit like this, where one's in the numerator, one's in the denominator, then if the bigger one's in the denominator, you're going to get 0. So that's kind of another way you can see this. Now, I want to give you guys a warning. It won't always be clear which function is higher on the hierarchy of functions, because sometimes you can combine 2 of the smaller ones, but you guys can team up and beat one of the larger ones. So if you're ever unsure about which one's higher, just use L'Hopital's rule instead. All right, so I want you guys to practice this now. And then I want to answer a question that I saw in the chat. So practice 2. So now I want you guys to do the limit as x goes to infinity of ln of x quantity squared divided by x. Why don't you guys take a little bit and do that? Got some people quick on the draw here. Looks like 0 is the answer. All right, seems like 0 or one of its variants is the going to be the answer here. Let's see if that is indeed the case, and if so, why? All right, so if we try L'Hopital's rule here, we see this is another infinity over infinity scenario, because natural log does go to infinity as its input does, and then as x goes to infinity, x goes to infinity. All right, so we can do L'Hopital's rule here. Let's do the easy part first and procrastinate. The derivative of our bottom will be 1. That's nice. And then the derivative of our top, we need to use the chain rule. So we have something squared, right? So the derivative of something squared is 2 times that something. And then we multiply by the derivative of ln of x, which is 1 over x. So if we tidy up a bit, we have 2 ln of x over x. All right, so it seemed like that x was able to creep back in there. So let's try to use L'Hopital's rule again and see if we can't fully get rid of it. So if we do the derivative of our top, we have 2 over x. We do the derivative of our bottom, we have 1. So this is going to be the limit as x goes to infinity of 2 over x. And now we're at this point where the top is going to be just 2, and then the bottom is going to get huge. So once again, we're going to have 0. So this ended up kind of being like the previous example here. All right, now one more thing I want to talk about before we get going here is other applications of L'Hopital's rule. So someone earlier mentioned, are there other situations besides these two in which we could use L'Hopital's rule? And the answer is yes. There are 7 situations in which you could use L'Hopital's rule. And these are called the 7 indeterminate forms. Every time I say that, I feel like a wizard or something. It's like, oh, beware the 7 indeterminate forms or something. I don't know. But here are all 7 of them. So we have the 2 that I mentioned above, 0 over 0, infinity over infinity. And this one, we could just use L'Hopital's rule right away. So what are the other ones that we can have here? Well, we can have 0 times infinity. If we have this scenario, we move something to the denominator. Because, for example, let's say I move the infinity to the denominator. Then I have 0 times 1 over infinity, or sorry, 0 times 1 over infinity. But then that's going to be 0 over 0. So moving something to the denominator here, whether it be 0 or infinity, will turn it into one of these two. That's how we deal with that. Infinity minus infinity, what do we do in this scenario? We usually use algebra or combine fractions in some way. And then we would turn it into one of these. So the goal for all of these indeterminate forms is to get to one of these two right here. And then finally, we have our exponential indeterminate forms. We have 1 to the infinity, infinity to the 0, and 0 to the 0. Each of these, what we do is we do something called the e to the ln trick. And what do I mean by that? I'm going to illustrate that in an example. So for example 5, but before I do this example, I want to say what these indeterminate forms really are. I like to think of indeterminate forms as where two rules of math kind of come head to head with one another. Like for example, normally if you multiply something by 0, you get 0. But on the other hand, if you multiply something by a massive number, you usually get a massive output. But what happens if those two forces combine? So normally if you subtract infinity from something, you're going to get super negative. But normally if you do infinity minus something, you're going to be really huge. So which way is that one going to end up? Now, when I say 1 to the infinity for this one, I mean something getting close to 1. Usually if we multiply something close to 1 by itself a bunch of times, it'll stay around 1. But if we accumulate enough of them, like maybe if you do 1.1 to the infinity, that will eventually get really huge, for example. So this could be a dire situation here. Usually if we raise something to the 0th power, we just get 1. But usually if we do infinity to any kind of positive power, we're going to get a huge number. So that's why this one doesn't work. And then 0 to the 0, 0 raised to a power is usually 0, but then anything raised to the 0th power is usually 1. So I like to think of this as like all of these kind of rules of math flying in the face of one another. And which way does it end up being? It totally depends on the situation right here. All right. Now people are making a bunch of anime references. I totally missed a lot of what happened here. Okay, anyways, let's go ahead and do our limit here. Yeah, let's do our limit. So we have the limit as x goes to infinity of 1 plus 1 over x to the x. Now, does anyone immediately know what this is? We've actually seen this before in a homework. What is this one? It's e, right? So this is e. And many mathematicians actually take this as the definition of e. E is the number that is the result of this limit. That is a very common way of defining e. But how do we end up getting e here if we don't take it as just a definition? Well, let's try to solve this limit out explicitly and see what happens. So if I try to plug in infinity right away, which one of the indeterminate forms will it end up being if I try to put in infinity right away? Yeah, it's going to be 1 to the infinity. That's right. Because if I plug in infinity here, this is going to be like a 0, and then I have an infinite up here. Okay, now, according to what I said earlier, I need to do something called the e to the ln trick. What on earth is that? Well, I hope you guys would agree that if you have something and you do e to the natural log of it, it's still the same thing, even though it looks radically different. And why is that? Well, remember, exponential functions are the inverse of logarithmic functions. So at any time, what I could do is I could just cancel these out and end up back where I started. So at any time, I'm allowed to do e to the ln of something here. Now, why on earth would I do that? That just makes this look way worse than it already did. Well, let's see. I have an exponent here, right? And exponents work pretty well with logs. They come to the front. So we have the limit as x goes to infinity of e to the x, ln of 1 plus 1 over x, like that. All right. Now, exponential functions are continuous, so you can move limits in them. So effectively, all we're doing here is we're worrying about what the exponent is, and then we'll just do e to whatever we get. Okay, now let's kind of recap what we have here. What type of indeterminate form is this now? I heard someone in the crowd say, what is that? Oh, yeah, infinity times 0. Looks like the chat has it too. That's right, because x is going to infinity, but then we have ln of 1, which is 0. So this is a 0 times infinity situation, and I claim that we need to move something to the denominator. So what do I mean by that? Well, what I mean is I'm going to take this x, and if I move it to the denominator, or if I move anything to the denominator, I need to negate its power, right? So this is ln of 1 plus x, and then we have x to the negative 1 down there, because this was x to the positive 1 up here, and we have x to the negative 1 down there. Why can you bring the e out of the limit? Because it's a continuous function. So you can move limits inside and outside of continuous functions. All right. Now, what does this actually look like? So this x to negative 1 is the same thing as 1 over x. So now if I plug in infinity, what am I going to get now? I'm actually going to get a 0 over 0 scenario here, because I have ln of 1, which is 0, and then I have 1 over something getting huge, which is also 0. So now I can finally just straight up use L'Hopital's rule. So now I'm ready for that. But we had to do some groundwork first. All right, let's procrastinate and do the easy part first. The derivative of 1 over x will be negative 1 over x squared, like that. The derivative of the top, I need to use the chain rule. So the derivative of log of something is 1 over that something. And then I multiply by the derivative of 1 plus 1 over x. The derivative of 1 is 0. And the derivative of 1 over x is negative 1 over x squared. All right, so there we go. There's our result of L'Hopital's rule. And it kind of made it look a little bit worse. We got rid of the natural log, but it looks a little bit worse. Now, there is one nice thing that we could do right away that's going to really help us. And what's that? Yeah, we could cancel, right? So I have a negative 1 over x squared I got from the derivative up here, and then I also have one down there. So those will just cancel out. And now let's see what we get. So this is e to the limit as x goes to infinity of 1 over 1 plus 1 over x. Now, if I try to substitute the limit in here, that's actually a limit I can do right now, because I have e and I have 1 over 1 plus, and then that limit will be 0. So I end up getting e to the first power, aka e. So for those of you wondering why that limit was e, that's why. It's because of L'Hopital's rule in doing this e to the ln trick. All right, I think we're about out of time. Oh, we're definitely over. Sorry about that. Anyways, next time we'll do the limit comparison test, and we'll put all of our limit practice to use. So I will see you guys then.